Okay guys, Assalamualaikum. Good afternoon. So today we will start a new chapter 3, which is Bipolar Junction Transistor, BJT. Okay. Okay, this is the chapter outline. So at the end of this chapter, you will be able to explain or you will understand the BJT structure, basic BJT operations, BJT characteristics and parameters, and the last one is BJT as amplifier and switch. Transistor can be used as amplifier or switch. It acts as a current controlling device. So these are the functions of the transistor as a current controlling device. Transistor can amplify signals, and the signal could be an audio signals or perhaps some high frequency radio signals. Transistor has an ability to do this without distorting the original inputs. BJT has three doped semiconductor regions: emitter, base, and collector. You write down E for emitter, B for base, and C for collector. And BJT is separated by two PN junctions, base collector junctions, and base emitter junctions. There are two types of BJT, which are NPN transistor and PNP transistor. So this is how we use all the symbols to represent NPN transistor and PNP transistor. However, in this chapter, we will analyze more for NPN transistor. Okay, these are the samples of transistor packagings. The most important thing is that we know which terminals is the emitter, base, and the collector. This information we can get from the datasheet models that will be given together with the components. Okay guys, as I said earlier, BJT has three regions: emitter, base, and collector. The terminals has been indicated by using the capital letter E for emitter, B for base, and C for collector. So these three regions are separated by two PN junctions. So these the definitions of what is the constructions of BJT. Okay. The functions of emitter is as a current supplier or carrier. For collector, C is to collect charge for circuit operations, and base acts as a junction that controls the current flow. Okay, there is one PN junction in diode, while in bipolar junction transistor, BJT, there are three layers and two PN junctions, which are base emitter junction, BE, and base collector junctions, BC. Base is lightly doped and it has a very thin current carrier, while emitter is heavily doped and it has more current carrier compared to B and C, while C or collector is moderated dope and it has moderate current carrier. Okay, what is a dope process? Dope process is the process to add a current flow ability to the region. So that's the dope process. Okay, illustrations of BJT actions. Okay guys, this will be a very long explanations, but we will do this together. Okay, please stay with me and hopefully at the end of this slide you will be understands the operation of the BJT. Okay. Okay, for NPN transistor, electron at emitter. Okay, so this E, emitter. This one is base. And this is collector. Okay, so electron at emitter is being pushed by the negative terminals of power supply. Mana power supply? Negative terminals of the power supply toward junctions into P-type base. Okay, so ni NPN, so ni N-type, ni P-type, this one is N-type. Okay, so electron at emitter kat sini, this emitter will be pushed by the negative terminal. So negative, electron is negative, will be pushed by the negative terminal toward junction into P-type base. So electron will be pushed to P-type base. Okay. Okay, as I mentioned before, base is lightly doped and very narrow. So it has a very thin current carrier. Okay, so only small percentage of electrons flow from BE junctions and can combine with the holes and flow out of the base lead as the valence electron, forming small base current IB. And most electron will diffuse into BJ junctions. Okay, BJ junctions, base collector, depletion regions. Okay, depletion regions, and forming a collector currents IC, which is larger than base current. So IC is greater than IB. And the emitter current IE is slightly greater than the collector current IC. So IE is greater than IC, slightly greater than IC because of the small base current IB that split off from the total current injected into the base region from the emitter. So therefore, the conclusion that we can make is IE Okay, the total current is equal to IC plus IB. Okay, so the current flow through emitter is equal to the current flow through collector plus the current flow through base. Okay, so these the detailed explanations for the previous figure of illustrations of BJT actions. Okay, for NPN transistor, electron at emitter is being pushed by negative terminal power supply toward junction into P-type base. So base is lightly doped and very narrow, so it has a very thin current carrier. So only small percentage of electron flow from BE junctions can combine with holes and flow out of base lead as valence electron, forming small base current IB. Okay, so the explanation for the previous slide. Okay, for both NPN and PNP, BE junctions, base emitter junctions is forward bias. Okay, the similarity of the NPN and PNP, while the BC junction, base collector junction, is reverse bias for both NPN and PNP. However, the bias voltage polarities, okay, the bias voltage polarities and the current directions are reversed between these two types, NPN and PN. The difference is between the polarity of the bias voltage and the current directions. Okay. Emitter current is sum of collector currents and base current, i.e. equal to IC plus IB. IB is small compared to IE and IC. Then we assume IE is approximately similar or equal to IC. Okay, transistor will be connected to DC bias voltage as shown in the figure below, NPN and PNP. Okay, so DC bias voltage, VBB voltage, VBB forward bias base emitter junction, VBB forward bias base emitter junctions, and VCC reverse bias base collector junction. And normally VCC is from power supply and VBB is from voltage divider. Okay, so this from power supply, VB is from voltage divider. When transistor operated within its linear limits, okay, so IC will be equal to beta IB, where beta is the DC beta, is a current gain of transistor. Okay, beta is a current gain of transistor, and the value of beta is within 20 to 200. Okay, so when transistor operated in the linear limit, IC equal to beta IB, where beta is a current gain of transistor and the value is within 20 to 200. Ratio of IC collector currents and IE emitter currents is alpha DC, where alpha DC is equal to IC over IE. And typically alpha DC range is from 0.95 to 0.99 and must always less than 1. In current and voltage analysis for BJT characteristics and parameter, there are 3 key DC voltage and 3 key DC currents, to be considered, which are, for current, we have IB, IE, and IC. While for 3 DC voltage, we have VBE, okay, base emitter, VCB, collector base, and VCE, collector emitter. Okay, analysis of this transistor is used to predict the value of DC voltage and the value of currents by using Kirchhoff law and there's a transistor beta DC. So this is the formula that we will use in order to analyze the circuit of transistor or BJT. So we have 1, 2, 3, 4, 5, 6 equations here. The first one, VBE equal to 0.7 volt. VBE equal to 0.7 volt. Equation number 2, VBB minus VBE equal to voltage across resistor RB. So here is VRB. VBB minus VBE equal to voltage across resistor RB. And VRB over RB is equal to IB. VCE equal to VCC minus VRC, where VRC is voltage across resistor RC, VRC. And VCE is equal to VCC minus IC, RC. Okay, voltage across resistor RC. And IC is equal to beta DC IB, and VCB is equal to VCE minus VBE. So this is the equation that we will use in order to analyze the BJT. If VBB is set to produce a specific value of IB and VCC is set to 0, then IC will equal to 0 and VCC is equal to 0. Now, as VCC is gradually increased, VCE will increase and so will IC. When VCE is increased and IC also will increase, as indicated between point A and point B. Okay, as VCE is increased, IC also increase. When VCE exceeds 0.7 at point B, the base collector junctions will become reverse bias and IC reach its full value determined by the relations IC equal to beta IB, where beta is equal to beta current gain of transistor. Ideally, IC level off to an almost constant value as VCE continue to increase. This action appear between point B and C. IC level off to an almost constant value. Okay, lebih kurang kat sini sahaja. But VCE continue to increase. By setting IB to constant value, additional IC versus VCE curve can be produced as shown in figure below. These curves constitute a family of the family of collector curve for a given transistor. A family of curves allow you to visualize the complex situations when the three variables interacts: VCE, IB, and IC. Okay, cut off. With IB equal to 0, when IB equal to 0, transistor is in cut-off regions, and practically there are no current flow in the collector part of the circuit. Okay, in cut-off regions, when IB equal to 0, transistor is in cut-off regions and there are no current flow. IB equal to 0. Very small collector leakage current, ICO, due to the thermals, and it will usually neglected. So VCE, and we assume VCE equal to VCC. Okay, so in cut-off region, IB equal to 0. So there are no current flow in collector part, and VCC is approximately equal to VCE. Saturation region. When base emitter become forward bias, IB will increase, so will IC, and VCE will decrease as result of RC. When VCE is saturated, base collector become forward bias and IC cannot increase, even IB increase. Once IC maximum, transistor is said to be in saturation, and by Ohm's law, IC saturated is equal to VCC RC. Cut-off and saturation can be illustrated in relation to collector curve by a load line. Ideal cut-off is IC equal to 0, and VCE equal to VCC. So here is the cut-off point. And saturation when IC equal to IC saturations, and VCE equal to VCE saturations. In between cut-off and saturation along the load line is active regions of transistor operations. Beta for a transistor is not always constant. Temperature and collector current both will affect the value of beta, as shown in the figure below. When temperature constant and IC increase, and temperature is constant, the value of beta will increase until maximum. Further increase IC value, beyond this maximum point, it's the maximum point, okay, will cause the value of beta to decrease. Okay, start to decrease after the maximum point. If IC is held constant and temperature is varies, B change directly with temperature. If temperature is increased, beta is increased and vice versa. Datasheet usually specify the value of B at specific IC value, and it varies from device to device due to inconsistencies in the manufacturing process. Okay guys, so that's all for part 1. We will stop until this slide, okay, before I continue transistor applications. We will discuss a few examples and tutorial questions in the next presentations and videos. Okay guys, thank you.